Hi, my name is Audrey Lee, and this is my final project video for ENME435 remote sensing at UMD, taught by Professor Stephen Mitchell. For this project, I designed, integrated, and tested my own LiDAR sensor, which is based on the Raspberry Pi and OpenCV platforms. The target that I chose to create a 3D map of is this Testudo statue in front of the business building, and I chose it because he is our school mascot. LiDAR, which stands for Light Detection and Ranging, is an active sensor that measures object distances by analyzing the reflected laser light to determine the distance of the object. It is used for high-res 3D mapping of things such as terrain or autonomous vehicles, and our specific camera LiDAR system uses the camera to detect where in the frame the laser is and computes the distance based on geometry between the sensor and the laser origin. So here's my setup with the line laser attached and powered by my Arduino, and this line laser is pointing forward horizontally and rigidly mounted 12 inches away from my Raspberry Pi camera. The camera is pointed in the same direction as it and is connected to my Arduino, and this whole thing is set on a tripod and can rotate upwards and downwards to scan. To calibrate the system, I'm using my Raspberry Pi to run a virtual environment and running a laser alignment picture to align the laser to these horizontal lines on the camera. This is very important as this helps ensure an even distance read from the left of the laser to the right of the laser. Here's the second part of my laser calibration process, where the number on the right of the image is how far my camera is from the wall. And this is to help make sure that what the program is actually outputting is the same distance as what it is in real life. And so here I'm adjusting the rho and RPC values to make the points align with the graph. So here's the original, and then here you can see I'm pulling up the final where it is aligned. With the system set up and ready to go, let's take note of some of Testudo's prominent features. He has a head sticking out of the front as well as two front legs, and his two back legs are also quite large with his little tail underneath his shell. He also has some textures on his shell and is generally shiny, and he's sitting on a podium in the middle of 3 different buildings that are shining onto him from the back, right, and left of him, and these will prove to be challenging. Here's my setup for Testudo, and I have my sensor and camera far enough from Testudo so that it will capture the entire thing in its frame. And here's how I'm measuring the different angles that my tripod is sitting at using an app on my phone. During my first reading of Testudo, I had underestimated how much the ambient light and shininess of Testudo would mess with my pictures, and that's why I have my friend holding up a towel in the back. It was a pretty pleasant encounter. Returning to my first attempt at mapping, here are the images that I took, and it seems that the 3-second exposure time wasn't enough, and the measures that I took to get rid of the ambient light also didn't help very much. So here is the first reading shown as a 3D point cloud from my Python script, and you can see there's a lot of noise and a lot of the features are not shown or picked up. And these are lessons that I took into my next reading to lessen the ambient light and also improve the laser reading. For my second attempt, the first thing that I did was to change my image exposure time from 3 seconds to 10 seconds. So here I'm testing that theory that the 10-second exposure time will create a much better image of the laser that I can later isolate better. So here, labeled 1 is the 10-second time, and you can see it's already much better than the 3-second one labeled 0. To improve the situation with the ambient light, I created a freestanding backdrop that covers more of the ambient light coming from behind Testudo, and I also did my research and bought some foot spray, which creates a thin layer of powder on top of Testudo, which reduces its shine and also doesn't have any lasting impact. Here you can see that with a wipe, it gets rid of all of the powder. For this attempt, it was actually raining and I had to wipe away the water from Testudo before, but the foot spray actually saved me here because it made him a lot less shiny than he was before. Here I'm getting the other angles, and unfortunately here was when it started to drizzle, So I moved as quick as I could and also had my friend help shield my actual sensor from dying. And of course, after mapping, I just needed to include that I cleaned up after myself, so there should not be any evidence of foot spray on Testudo. To port all the images over from my Raspberry Pi, I used WinSCP, and this just helped get all of the images from my Pi onto my computer. These are the images that came out from this attempt, and you can see they're a lot better than the first attempt. The laser is much clearer, but there are still some shiny areas on Testudo that will cause some noise on the actual reading. I took measurements 1 degree apart on actual Testudo, and then I fanned that out to 2 degrees and 3 degrees as I got farther away because it's just one solid block underneath. To isolate the laser line on the image, I used a color picker and chose HSV values to isolate just the red line on the image and try to get rid of as much noise on the edges as possible. And here I'm running the Python script that creates a text file and a 3D point cloud of all the XYZ coordinates that are taken from the isolated laser line on the image and calculated to become a distance away from the camera. So here are all the angles of the readings that are coming out straight from my Python code. And there are a couple improvements that I want to make. So here are the improvements that I put in my Python script. I have different regions for different HSV lighting and values that I need, and then also a filter that gets rid of values that I know aren't mapping Testudo. So here is a reading of Testudo before I created different HSV values, and here's the after. You can see that it gets rid of a lot of ambient light and also includes more of the lines. Here I'm calculating by clicking points on the extremities of Testudo to find the parts that I want to keep and filter out, and here are some examples of where I filter out the extra noise. With the 4 angles of Testudo cleaned up, I'm using Cloud Compare so that I can put the 4 parts of Testudo together, and this gives me a better idea of the transformation matrices that I'll need in my MATLAB to create the final point cloud. Here are the transformations in MATLAB, and because they use different conventions, the values are not exactly correct. And here I'm just making additional transformations and tuning them so that I can create my final MATLAB point cloud. And here's my final Testudo point cloud on MATLAB. I think it came out pretty well, as you can see his head and 4 legs as well as the shell very clearly. You can also kind of make out his tail, and it's clear that he's sitting on a podium. There's still quite a bit of noise here and there caused by the light, and the podium is not exactly straight. To see how accurate this was to the actual thing, I took measurements at the front of Testudo, and I measured 36 but saw 34 in the point cloud. I measured 30 but saw 26 in the point cloud, and measured 51 but saw 50 in the point cloud. This error is probably due to human error with the angles as well as calibration issues, but here you can see in the overlays that it's pretty true to Testudo. The last thing I did was to create a mesh using the point cloud in MeshLab. I'm simplifying the points and deleting those extraneous points, and then I created the normals, adjusted those, and created the mesh using a screen Poisson. So here it's not exactly perfect, but you can still clearly make out Testudo's head, 4 legs, and shell. Overall, I was very happy with the final point cloud that I made of Testudo, but more so all of the lessons that I learned and all of the challenges that I overcame to create this.